Everyone I know is like, oh man, I'm bored. I'm gonna go watch a movie. It's not like, oh, I'm gonna do.
Okay. So I'm going to get started again. So I'm now going to be moving on to talk about section 5.3, which is called the fundamental theorem of calculus. So the fundamental theorem of calculus is really the connection between these topics of integrals which I've talked about so far and the idea of derivatives that you've learned in Calculus 1. One of the things to mention is that, again, while calculus itself as a discipline didn't exist until the 16th century, derivatives existed before that. People found derivatives before that. Integrals also existed before that. People found areas, right, by doing stuff like those limits of sums that I did so far. The real difference between, stuff that happened before the 16th century and stuff that happened in the 16th century and afterwards were that people recognized the connection between integrals and derivatives, the connections between finding slopes and finding areas. And one of the people who was important to recognize that connection was Isaac Newton. He's one of the people who's credited with the founding of calculus. And for those who've taken physics, you also know his name from physics. There's no coincidence that it was someone who did a lot of his work in physics who was important in the development of calculus. Because the idea is that one of the big discoveries that happened that led to the invention of calculus was the discovery that the machinery of Riemann sums, the stuff we've done so far for calculating areas, can also be used to calculate distance traveled. So the idea is, suppose we're traveling from here to Vancouver. And suppose we know that we're not always driving at the same speed. Right? If we're driving at the same speed, it's easy to calculate how far we've traveled. Let's suppose that we're accelerating as we're driving on the highway. We're driving faster and faster and faster. So that we know that our speed is, let's say it is 3t, where t is the time that's passed. So after 1 second, we're going 3 kilometers per hour. After 2 seconds, we're going 6. Okay, let's make it 10t. But more reasonable. 10 kilometers an hour after the first second, 20 after the second, 30 after the third second, etc. And the question now is, how far have we traveled after 10 seconds? Right? Well, one way of measuring this, how far we travel after 10 seconds, is we can talk about what's happening in the first second, what's happening in the second second, what's happening in the third second, etc., separately. The first second is the interval from 0 to 1. Second second is the interval from 1 to 2. Third second is the interval from 2 to 3, etc. In the first second, we can, let's say, okay, halfway through this second is t equals 0.5. Right? So about in the middle of this time, we're going to time is 0.5, so our speed is 5 kilometers per hour. So approximately, we're going close to 5 kilometers per hour throughout this time. We want to measure the distance traveled. Distance traveled is always the speed times the time. So the distance is the speed, which is 5, times the amount of time in the second, which we can call delta t, or we can call 1. Here, you know, we can take a time in the middle of a second. We can measure the speed, which is 15 kph. So the distance is going to be 15 times 1. We can do the same thing here. The key thing is that the method that we're using to calculate, and then we can, if we want to find total distance traveled, we can do is we can add all these distances together. This method that we're using to calculate distance turns out to be exactly the same method we use to calculate area. So when we calculated area, we took an interval, we divided it up into pieces, and each piece we picked what's called a test point. We're doing the same thing here. We're taking a different time at each piece. You could calculate the height of the rectangle in each piece. How did you calculate the height of the rectangle in each piece? You plugged the test point into the function. Here, we're plugging the time into the function to get the speed. When we're calculating areas of rectangles, we multiply each of those heights by the width. The width here represents the time passed. If we multiply each of those speeds by the time passed, we get the distance. And then we get the total area, we add all those up. Same thing's happening with the speed. You get the total distance traveled, we add all those things up. The idea is that the process of calculating area is the same as the process of calculating area from a height function is the same as the process of calculating distance from a speed function. So the idea is to measure velocity. We're going to take some sample time, we're going to plug it into the velocity function. To measure the displacement, the distance traveled, we take the velocity function, multiply it by the amount of time in each interval. If you want to measure the total displacement, we're going to have to add all those things up. And it turns out if you want to get a better and better approximation of the speed, one thing we can do is use more and more intervals of time. Divide up your length of time more and more precisely, which will make these guys better and better approximations of the actual speed during those intervals. So it turns out this formula for the limit of Riemann sums works just as well for measuring displacement or distance traveled as it does for measuring area. And that's one of the things that the 16th century physicists noticed, is that the same process for calculating area can also be used for calculating displacement. What this means is when they saw an integral sign like this, they thought, okay, this integral doesn't only represent area, it also represents distance traveled. If we're integrating a velocity function, this integral represents the displacement between time A and time B. Now, the importance of this is that you already know something about velocity functions. In Calculus 1, you've learned that velocity is the derivative of position. Right? There's a relationship between displacement and position. If the position at time A is 0, then the displacement between time A and time B, the distance traveled between time A and time B, is the same as the position of time B. So if you want to get the position at time B, all you've got to do is you've got to do an integral from A to B and just make sure that position at time A is 0. But velocity is the derivative of position. Since an integral gives you position, that means the derivative of that position should give you the same velocity function that you started with. So the idea is that there is the relationship between derivatives and integrals, the relationship between differentiation and integration is what's called an inverse relationship. If you start with position and you want to calculate velocity, the velocity, what you've got to do is you've got to do the process of differentiation. Here, I'm going to write like this. So velocity there, and then I can write the word differentiation. If we have velocity, we want to calculate position, we've got to integrate the velocity function. We've got to do the process of integration. So the process of differentiation goes one way, the process of integration goes backwards. So derivatives and integrals are opposites of each other. To go one way, we differentiate, we find a derivative. To go the other way, we integrate. We find an integral. And that's exactly what the fundamental theorem of calculus says. It says that derivatives and integrals are each other's opposite. The differentiation and integration are what are called inverse processes. So there's two different parts of the fundamental theorem of calculus. The first part is what I'm going to cover today. The second part I'm going to cover in Tuesday's class. So the first part of the fundamental theorem of calculus gives you a way to evaluate the derivative of an integral. So how do we calculate the derivative of an integral? Well, that's what the first part of the fundamental theorem of calculus is going to tell you. Does anyone know what the derivative of this integral is going to be? X squared. And this is basically what I was sort of saying before, is if you integrate and then you differentiate, if you take an integral and then a derivative, you should always get back exactly where you started. So what's inside is t squared. We take the derivative of the integral, it'll just give you x squared. So that's sort of the simple form of what the fundamental theorem of calculus tells you. But the first thing I'm going to do before I even get into that is I'm going to talk about what does it mean to take an integral where the upper end point is an x rather than a number. What does that actually represent? Well, that means is where you're stopping the integral is going to depend upon what x is. Now again, one way of interpreting this is that if a, again, is that time where the position is 0, the integral from a to x gives you position at time x. And that gives you what's called the position function. So a couple different ways. Another way of thinking about it is that g of x represents the area between 0 and x. And what g of x is, what that area is going to be, is going to depend upon what that point x represents. So if we want to find the maximum of g of x, we want to pick an x that will make that area as big as possible. If we want to find a minimum, we want to pick an x that will make that area as small as possible. So I'm going to do an example of this from the textbook. And again, this is one of these ones I'm going to have to draw on the board. There's the graph of the function that we're dealing with. So g of x is the integral from 0 to x in this case, of this graph. So if 0 is here, x is wherever we're going to stop. So the first part of the question asks us to evaluate g of x for x's 1, 3, and 5. So first thing we're going to evaluate is g of 1. G of 1 is the integral from 0 to 1 of f of t dt. So that means we're starting at 0 and we're ending at 1. And we're calculating that area. That area is a triangle. Its base is 1, its height is 1. So it's a half times 1 times 1, which is a half. If you want to find g of 3, that means we're integrating from 0 to 3, this function. That means we're starting at 0, we're ending at 3. So then we're going to take this area minus the area below. Area above minus area below. That's going to be 1/2 minus that area below has base 2, height 1. So 1/2 times 2 times 1. 1/2 times 2 is 1. 1 times 1 is 1. 1/2 minus 1 is negative 1/2. If we want to find g of 5, g of 5 is the area from 0 to here, which is 5. That means we're going to take this triangle, we're going to subtract this triangle, and we're then going to add that triangle. So we're going to have 1/2 minus 1 plus, for that triangle has base 2 and height 2. So it's negative 1/2, 2 times 2 is 4, plus 1/2 is 2, which gives you 1.5. The next part asks us to estimate what g of 7 is. So the key thing is that this curve here is not something we can, it's not a triangle, so we can't easily calculate its area. So we want to know approximately how big is the area up to here. Well, we know what the area is up to here. We want to calculate, so then we really just want to find out what this blue area is approximately and add it on. Well, in this blue area, I can fit 1, 2, 3, 4 and a half, and a bit more than a half of a grid square. Right, so this is approximately 1, 2, 3, 4, 5. Right, that blue area is approximately 5. And if you look at the picture in your book, you can sort of see that like if you try to figure out how many squares are in that little blue piece, it's going to be approximately 5 squares. So g of 7 is approximately 1.5 plus 5, which is approximately 6.5. Again, you can get better estimates if you do more than just sort of count approximately how many squares are. But if you're going to estimate it, that is really usually good enough. So part C, we ask, where does this thing have a maximum? Where is the area going to be as big as possible? Well, the idea is that the more of this positive area we take, the bigger the area is going to be. So if I want to take as much area as possible, I'm going to go all the way up to there. Right? So g of 7 is a maximum. If you want to find a minimum, we want to take as much of the negative area as possible and none of the positive area, or as little of the positive area as possible. To do that, this is usually the best interval to pick, right? This interval gets all the negative area, but it only gets a little tiny bit of the positive area. Now, we can't do from 1 to 3, because in this function, the 0 on the bottom is fixed. It's only this x up here that we have control over, which is why we want to take a minimum. We're going to go from here to here. That has as much of the negative area and as little of the positive area as possible. So g of 3. I'm going to get rid of this black marker. I've got another one somewhere. There we go. G of 3 is a minimum. And then they want us to sketch a rough graph of this function. Well, g of 0, if we go from 0 to 0, that's going to be no area at all. At 1, we are up at 1/2. At 2, well, actually we're going to be, well, at 3, we know we're down at -1/2. At 5, we're up pretty high. We were at 1.5. At 7, we were approximately at 6.5. So a rough graph of this will look something like that. Right, again, those points that I got on there in sketching that graph were the things that I calculated in parts A and B. Right, I said A, g of 1 is 1/2. G of 3 is -1/2. G of 5 is 1.5. Those are all done by calculating areas. G of 7 is going to be 6.5 approximately. That's what and sort of connect the dots and give you a sketch of this g of x function. Again, this g of x function represents the area from 0 to x. It is a function. It can also represent, if this is a velocity graph, that g of x will represent the distance traveled. If that helps visualize what that actually means. Any questions about this example? Okay. So, one of the reasons I talked about these functions is because I wanted to sort of say, what does it mean to take the derivative of this function? Well, the derivative of this function means we're going to talk about the slope of this graph. Well, the slope of this graph will actually turn out to be the same thing as this graph. If we actually calculate the slope of this graph at here, the slope of this graph is 0 at x equals 3. If we look at this graph at x equals 3, this graph is 0 there. The slope of this graph is approximately -1 here at 2. If we look at 2 on this graph, 2 is down at -1. Right, so the slope of that graph is the same as the y-coordinate under this graph. The y-coordinate of that graph is the area under this graph. And because basically the integral of the velocity gives you a position function, the derivative of the position function gives you a velocity function back again. The derivative of an integral will always give you just the function inside. Now this rule is called the fundamental theorem of calculus part 1. So if you take the derivative of an integral, it gives you the function inside. This rule only works if the bottom of the integral is a number and the top of the integral is an x. This is the only case in which this rule works. If this rule is something else, it's going to be a little bit more complicated than that. So example 2 is a case where I can just use this rule. Here I want to find the derivative of that function there. So I want to find the derivative of the integral from 3 to x of e to the t squared minus t dt. Well, the rule says the derivative of an integral from a number to x is just a function inside. So I'm just going to write out that function inside, but I'm going to replace the t with an x. That's my answer. That's what the derivative of this thing is. The reason we have to replace that t with an x is because this thing we're taking the derivative of is a function of x. So its derivative should also be a function of x. Right? If we had took the derivative of x squared, it would be 2x. It would be 2t. Right? This thing we're taking the derivative of is a function of x. It's not a function of t. So its derivative should also be a function of x. So again, this is like a new derivative rule that you just learned. Derivative of an integral sign. If the top is an x, the bottom is a number, you can just replace the t inside with an x. That's sort of like a new derivative rule. Another way of thinking about this. Any questions? Yes?
What if it's like number 17 where you have x on the bottom?
Next slide. So, oh no, sorry, one slide after this one. Sorry, it'll come up shortly though. So the next thing I'm going to talk about is what happens if rather than an x, something a little bit more complicated than an x. Well, the idea is whenever we have a derivative, and instead of an x, we have something more complicated than x, there's a derivative rule we need to use. That rule is the chain rule. So the idea is, whenever we're doing a derivative, and rather than just having an x on the top, we have like a 2x or an x squared or a sine x, we're going to have to multiply by the derivative of that little complicated thing. So we replace the complicated thing involving x with a u, take the derivative with respect to u, and multiply by the derivative of u. That's sort of one way of thinking about the chain rule. It's the way I teach the chain rule when I teach Calculus 1. If you know another way of doing the chain rule, totally do it the other way. I'm not saying that this is the way you have to do it. It just makes, it just happens to be the way that I teach it. So, here, the function is h of x is integral from 1 to square root of x of z squared over z to the 4th plus 1 dz. So the first thing I think is I wish that square root of x was just an x. Right? So what I'm going to do is I'm going to think in my brain that u is square root of x. Right? So really, I can think of h of x as the integral from 1 to u of z squared over z to the 4th plus 1 dz. Now, if I do the derivative of this with respect to u, I just take the u and I plug it in. But then I have to multiply by the derivative of u. So this is, sorry, I'm going to write that out again. Here, h prime of x equals u squared over u to the 4th plus 1 times u y. Some people have a hard time understanding this way of thinking about the chain rule. What I'm doing when I'm thinking about the chain rule this way is I'm saying, okay, let's say I want to take the derivative of e to the 2x, right? The idea is what I'm doing is I'm going to replace the 2x with just a u. I do the derivative of this with so here y is e to the 2x, y is e to the u. If I want to find y prime, I'm going to do the derivative of e to the u with respect to u, which is just e to the u, right? The derivative of e to the u is e to the u. But then I have to multiply by the derivative of u, which is u prime. E to the u is e to the 2x, u prime is 2. Right, so that's why. So same thing here, if I'm using the chain rule, this square of x I wish was just a u, replace with the u, take the derivative with respect to u. Once I've done the derivative with respect to u, I have to multiply it by u prime. And that will mean that h prime of x here will be u is square root of x. So I'll have square root of x squared over square root of x to the 4th plus 1. And I've got to multiply by u prime. Since u is square root of x, u prime is 1/2 x to the negative 1/2. It's the derivative of square root of x. You know, I'm going to do this. Can I get this? There we go. That's more visible. Anyway, so that's the finishing of the one I started on the other side. And this is just another example to explain the chain rule that way. Any questions about how I did this example? If it helps you to just remember, if I have that when you're taking the derivative, and this is not just an x, you have to multiply by the derivative of whatever this thing is on top, that also works. Right? Basically, you're doing this derivative as if this thing was just an x, so plugging this thing in, and then multiply the derivative of square root of x. Okay. I will do a couple more examples. Just want to check if there's any question before I move to the next slide. Great. Okay. So the next couple examples both involve this chain rule that I've just done, but they also involve what happens when your limits of integration are not just, you know, a number on the bottom. So, for example, we could have, rather than having here, we had a 1 on the bottom, we had a square root of x on the top. What would happen if it was the other way around? We had a square root of x on the bottom and a 1 on the top. Well, the answer is we know this rule that we can always switch the limits of integration as long as we multiply a thing by negative 1. That is the reason I brought up that rule earlier in today's class. You can always switch the limits of integration as long as you put a negative sign in front. You multiply the whole thing by negative 1. Now, if we have both a square root of x on the top as well as like an x on the bottom, then we're going to need one of the other rules I talked about, which says that if we have an integral from something to something else, we can always split it up in a middle point. We have from 0 to 4, we can always express as the integral from 0 to 2 plus the integral from 2 to 4. So that's the strategy we're going to need if we have x expressions involving x on both the top and the bottom. Wait a second. There we go. So example 4, I'm just going to do make that visible right like that. Is y equals the integral from sine x to 1 of 1 plus t squared, square root of 1 plus t squared dt. So we have here the integral sine x to 1 square root of 1 plus t squared dt. So the first thing I'm going to do is I'm going to say, okay, I don't need sine x to the bottom, I prefer sine x to the top, so I'm going to multiply the whole thing by negative 1 and switch the limits of of integration. The next thing I'm going to do is I'm going to say, okay, that sine x, I wish it was just an x, so I'm going to call it u. So this is really the integral from 1 to u, square root 1 plus u squared dt. And so then if I want to do the derivative of this guy, right, if I want to find y prime, what I've got to do is I first got to do the derivative with respect to u, which means I take this u up top and put it in where the t is. And then I've got to multiply by u prime. Now u here was sine x, so u squared will become sine squared x. Because u is sine x, u prime is cos x. So the derivative is negative square root 1 plus sine squared x times cos x. Any questions about this example? Okay. Oh, there we go. I was like, there's one more example for today's class. What happened to it? I must have hit the right arrow twice. So example 5 is the last one I'm going to be doing today. So example 5 is one where both the lower limit and the upper limit are complicated things. So the key thing is I want to find the derivative of the integral from 1 minus 2x to 1 plus 2x t sine t dt. So the first thing to mention is if both limits have x in it, I want to split this up as two separate integrals. If I want to integrate from here to here, I can do it by integrating from here to 0 and then integrating from 0 to here. And it turns out it doesn't matter if 0 is actually between those two numbers or not. If it's not between those two numbers, I'm integrating from here to 0 and then integrating from 0 to here, and this part where it went down before it went back up again is actually going to cancel itself out. So the key thing is you can just sort of write this as the integral from 1 minus 2x to 0 of this thing, plus the integral from 0 to 1 plus 2x of this guy. The first one I can write as negative the integral from 0 to 1 minus 2x. This 1 minus 2x I will think about as u. This 1 plus 2x I can think about as v. And if I want to do the derivative of this first thing, it's going to be negative u sine u times u prime. The derivative of the second one will be v sine v times v prime. Because the first one is the integral from 0 to u. So its derivative is going to be, plug the u in, multiply by v prime. Second one is the integral from 0 to v. So it's going to plug v in, multiply by v prime. And again, I'm going to have to do the last step over here. That means your final answer, u is 1 minus 2x. Oh, there's a negative sign in front. So negative 1 minus 2x sine 1 minus 2x times u prime turns out to be negative 2. Plus 1 plus 2x sine 1 plus 2x times the derivative of v is positive 2. And that's going to be your final answer.
So you never want us to go farther than that?
If you want to, go for it. As far as I know, WebAssign never requires you to go farther than that. I don't require you to go farther than that. If you want to, like, yeah, I mean, you could do more algebra. To be honest, I am not going to be doing it in my examples to save time. And same thing is true like on tests. If you don't want to, you don't have to. Annoyingly, the back of the book oftentimes does simplify more than I do, in which case sometimes checking your answer in the back of the book might cause difficulty. But yeah, if I really want you to simplify something, I will specifically say, and then simplify your answer, you know, on the test or quiz or whatever. Okay. So I just want to mention a couple things before I give you the group problems. So again, I'm going to do 5.3.2 next class. The first thing to mention is that there is a quiz on Tuesday in class. This is your first quiz. It covers sections 4.9, 5.1, and 5.2. Again, just to mention, there are things in the textbook that are not going to necessarily be on the quiz. If you want sort of a preview of what sort of questions I could ask on the quiz, look at the ones that are on the handouts I've given from those sections, so 4.9, 5.1, and 5.2. There will also be a WebAssign quiz that I will create shortly. And the WebAssign quiz will be due Monday. So the idea is you should be able to finish it in time that, like, you will get feedback on your stuff, and you can use that feedback to help study for the in-class quiz. The in-class quiz is worth more than the WebAssign quiz is. But again, I'll create that WebAssign quiz after class today. It'll be 3 questions I'm going to choose at random from the 4.9, 5.1, and 5.2 WebAssign homeworks. Again, you don't have to do all the homework problems if you don't want to, but you should at least try some of them before you try the quiz, because the quiz is going to have a time limit. So, and the homework ones will give you more hints and stuff like that. So, so that's one of the things I wanted to mention. Otherwise, today I will remember to hand out those Muddy's point cards. But I'm going to throw you up a couple of group problems to work on for the next 10 minutes-ish. Ignore number 3. We didn't get to that today. Again, I was a little bit overly optimistic. I mean, no, I was definitely overly optimistic with the plan for today's class. I didn't get through all that. That's okay. It's not going to throw us behind in the long run. But don't worry about number 3. We haven't actually gone over that yet. Just try numbers 1 and 2. Oh no, that's never mind. Yeah, that's fine.